Greetings all. Let's look at these two chemical structures again. The chemical on the left is 2-phosphoglycerate, and the chemical on the right is 3-phosphoglycerate. 2-phosphoglycerate has a slightly higher Gibbs energy of formation under standard conditions than 3-phosphoglycerate, because the negative charges on the phosphate group are just a little bit closer to the negative charge on the carboxylate group. How much higher? About negative 4.4 kilojoules per mole when the reaction is going in this direction, which is the same as saying it's positive 4.4 kilojoules per mole when the reaction is going in the other direction. Remember that delta G naught is always products minus reactants and is always done under standard conditions, and therefore delta G naught is a constant. Do the experiment under standard conditions, write down the number in a book, and then look it up again later if you need it again later. The equilibrium constant, KEQ, is the concentration of the products divided by the concentration of the reactants, which we can also calculate as KEQ equals e to the power of minus delta G naught over RT, where R is the gas constant and T is the temperature in Kelvin, or turning that equation inside out, delta G naught is minus RT natural log of KEQ. For the reaction in this direction, KEQ is about 5.9. At equilibrium, then, we should have roughly 6 molecules of 3-phosphoglycerate for every 1 molecule of 2-phosphoglycerate. And if we don't have that roughly 6-to-1 ratio, then we're not at equilibrium. And when we're not at equilibrium, the ratio of products to reactants has to have a different name. We call it Q for the reaction quotient. If we know what Q is, we can calculate the delta G. Delta G is RT natural log of Q minus RT natural log of KEQ. And our rules of algebra, we can simplify that a little bit to RT natural log of the ratio Q over KEQ. We'll look at 4 cases here, with a number of orange dots representing the relative concentrations of 2-phosphoglycerate and 3-phosphoglycerate. Our first case, Q is 4 divided by 24. KEQ is 5.9, because KEQ is always 5.9 when the reaction is in this direction. So delta G here is RT natural log 4 divided by 24 times 5.899, etc., which is around negative 8.8 kilojoules per mole. This reaction is exergonic, or spontaneous, or favorable when we're going in this direction, which is what we would have guessed because we have way too much 2-phosphoglycerate compared to equilibrium. In our second case, Q is 14 on that side and 14 on that side, so Q is 14 divided by 14, which is 1. Delta G, RT natural log of 1 over 5.899, etc., which is negative 4.4 kilojoules per mole, which might sound familiar. Case 3, Q is 24 divided by 4, which is 6. Delta G is RT natural log of 6 divided by 5.899, etc., which is around 42 joules per mole. Notice it's not kilojoules per mole this time, but just plain old joules per mole, and 42 joules per mole is very close to 0. Our fourth case, Q is 27 to 1. Delta G is RT natural log of 27 divided by 5.899, etc., which is around positive 3.8 kilojoules per mole. This reaction is endergonic, or not spontaneous, or not favorable, because this time we have too much of the 3-phosphoglycerate. If we want to look at these cases when the reaction is going in the other direction, all we have to do is change the sign on the delta G. Case number 4 is not spontaneous in this direction, therefore case 4 is spontaneous in the other direction. Summary. Whether the reaction is spontaneous or not depends on what the concentrations are right now relative to equilibrium. If you have too much 2-phosphoglycerate relative to equilibrium, then 2-phosphoglycerate to 3-phosphoglycerate is spontaneous. And if you have too much 3-phosphoglycerate relative to equilibrium, then 3-phosphoglycerate to 2-phosphoglycerate is spontaneous. If the concentrations are at equilibrium, then delta G is equal to 0. This is how we can have the reaction be spontaneous in this direction for glycolysis, but the reaction spontaneous in the other direction for gluconeogenesis, because it always depends on where you are right now relative to equilibrium. Okay, that's it for now. Thanks very much. I'll talk to you next time.